Okay, so let's start. See, we will introduce group action and Silas theorem today. We will go a bit fast with this abstract algebra. This is going to be the course with the most pace because metric space I am going quite slow. Measure theory we will go slow a bit as well. Not too slow, but a bit slow. Linear is I am going quite thoroughly, but the problem here is if I have to teach you group theory, then ring theory, I mean in total, then Galois theory, then it will take a year to complete the course. So I will have to go a little bit fast, but just let me start by saying this, that first I write two propositions. Tell me whether they are true or not. If G is a finite group, then G is embedded in Sn for some n. That is, there exists phi from G. This is an injective map. Okay, this is a sign of injection. Injective homomorphism. Is it true? Is it true?
হ্যাঁ দাদা এটা ঠিক হবে।
Yes, it is true. And I don't know if you remember the proof or not. Suppose mod G is K. We enumerate G's elements to be G1 to Gk. Okay. And then we use left regular representation. Okay, so I won't go into much detail because that will squeeze up a lot of timing. We will have to solve a lot of problems. Proposition. But if you want to know the proof, then tell me. I will write it in a paper and send you. Okay. Don't hesitate to ask for the proof. Proposition 2. If G is a finite group, then G is embedded in An for some n belongs to natural number. We will have to use left regular representation here. So An for some n. Is it true? Is this second proposition true? I think this question is more non-trivial. Is this true? So enough to show that any Sn is embedded. Sorry, I should write Sm is embedded in An for some n, right? Once we show that for every m, Sm is embedded inside some An, then G is of course embedded inside M, right? So take n equals to m plus 2 and define an injection from an to an plus 2 by you send an the elements of an to an. I mean, we should write like this: sigma goes to sigma if sigma belongs to an, sigma goes to sigma composition n plus 1 n plus 2 if sigma does not belong to an. First tell me, is it a group homomorphism? Consider it theta. Let theta be the mass. Is it a group homomorphism? It is a group homomorphism, okay? Because you can see actually if sigma tau both belongs to an, then theta of sigma compose tau is sigma compose tau, because sigma compose tau belongs to an as well, that is theta compose sigma into theta compose tau. If sigma tau none of them belongs to an, then they are both odd cycles, right? So sigma compose tau belongs to an because they are both odd cycle. The product is an even cycle. So sigma compose tau is again sigma compose tau, but we write it like this. This is a 2 cycle, so its order is 2. Since these are disjoint, see, tau doesn't have, has, understood, tau belongs to Sn. So of course n plus 1 and n plus 2 doesn't appear in tau, right? So these are disjoint cycles, hence they commute. Now you can write theta compose sigma theta compose tau. If sigma belongs to an and tau does not belongs to an, then sigma compose tau doesn't belong to an because this is an odd cycle. So theta of sigma compose tau is sigma compose tau n plus 1 n plus 2. Now sigma you write like this and then you write like this, that is theta of sigma theta of tau. Okay, so theta is a group homomorphism, understood? And theta is injective. Check that theta is injective. Okay, which implies Sn is embedded in a n plus 2. So as you have G from Sn, there is phi, then there is theta. So theta compose phi is is the embedding of G inside an plus 2. Understood? So these now we can start group action. Okay, these are some things which I wanted to tell. Let G be a group and S be a set. An action G on S is a mapping from G cross S to S such that G comma S goes to G times S. Of course, GS has to be in S. Such that this hold, like G1 G2 S is G1 then G2 of S. Like this is transitive. This is transitive. No, this is associative. Like acting G1 G2 on S is same as acting G1 on G2S, and ES is S. Okay. So there are a few examples, like H is a subgroup of G, and you are acting H on G by multiplication. There is another action, like H acting on G by HG H inverse. This action is called left multiplication. This action is called conjugation. We will use these actions very usefully. One immediate thing we should notice is that G is S here and H is G here in our definition as above. But see, H is acting on G in many ways, right? So there may not be a unique action from a group on a particular set. There may be more than one actions. Now they are acting S is G mod H here. They are acting G on the left cosets of G of H. Okay. S can be the set of all subgroups of S. Then again they are acting G on S by this conjugation. These are the actions we will be using in our proofs. Don't worry, we will not go into the very much details of those proofs, but what we will do is see a few nuances of the things. G be a group that acts on a set S, and the relation on S defined by X is related to X prime if and only if Gx is related to G prime. Gx is equals to G prime, okay? So G be a group that acts on a set S. The relation on S is defined by, so G, already you have G acting on S, okay? Some use this notation like G acting on S. This is also a notation. They are trying to give an equivalence relation on S by saying X is related to X prime if there exists a G such that Gx is X prime, okay? For X belongs to S, Gx is all those G belongs to G such that Gx is X, okay? This is called stabilizer of X, and this is called the orbit of X, okay? Orbit of X is a subset of set S, and stabilizer of X is a subgroup of G, okay? So to check that this is a subgroup and this is an equivalence relation indeed, these are not very troublesome work. Hope you can figure it out. Yes, that's what I want. So class of X, like theta X, yeah, they have defined it to be the orbit of X. See, they have fixed this X belongs to S, okay? Now they are taking all G and they are seeing what is Gx. They are collecting all the Gx's, okay? For a fixed X, they are collecting all Gx. Is called the orbit of X. Gx is called the stabilizer of a G. Now they say that G is to Gx is the cardinality of G is to Gx. Since this is a subgroup, we can do this by Lagrange's theorem. Gx divides G. By Lagrange's theorem divides G is theta X. So why should it happen? Like, hello.
GX
Gx
Hello?
was defined like this. Gx was defined like this.
Watch.
Oh.
GX.
Okay. Is Doipayan here in the class? Is Doipayan here in the class? No, I think so. So as far as I am seeing, Otim is not in the class, right? Otim is not in the class. Shrina and Tiyasha are not in the class. And Ognidipto, Doipan and Ritik is not in the class either. I think because of Bhaifota. Okay, so let's prove this. So what is T? T is the set G mod Gx. Okay, the set of all left cosets of Gx in G. They are defining phi from T to theta x, and they will show that this is a bijection. So Gx, this is the left coset of Gx in G. They are sending it to Gx. Okay. So first of all, see that this is a well-defined action, because if Gx is G1 Gx, G1 inverse G is in Gx. So G1 inverse G of x is x, because Gx is the stabilizer of x. So then you get Gx is G1x, which is theta of Ggx is theta of G1 Gx, right? So theta is well defined. I mean, sorry, they have noted it by phi. Sorry. Okay, phi is well defined. And also, if you take Gx equals to G1x, by reverse procedure you get this, then reversing you get this, and then reversing you get this. So phi is well defined and injective. Now you have to show that it is surjective. That's quite easy. Take Gx from theta x and see that phi G of Gx is Gx. So phi is a bijection. So T and theta x have same cardinality. Okay. Now let G act on a set S. I have shared these notes with you, I think. Let G acts on a set S. Then cardinality of S is summation of theta x, all these elements. Okay. Is it obvious to you? Is it obvious to you why this happens? Because if you remember, we already had defined an equivalence relation on S. So what does an equivalence relation do? It partitions the set, right? It will partition the set S. That's the reason this is happening. Okay. If we consider the wait a minute, they are probably going to class equation we are going to prove now. So now G is acting on itself, okay, by conjugation. So GH goes to GH G inverse. Here it is S, okay. from our definition. Now theta x is all those g such that gx g in, theta x is gx g inverse for g belongs to g, number of conjugates of x, and gx is all those g such that gx g inverse is x. But this means gx is xg, right? So all those elements which commute with x, that is the centralizer of x in G. Okay. Just a short notes. We have rightly shown that G mod Gx cardinality is of theta x, right? Right. So Gx here is Cgx. Thus we get G is Cgx. This is the cardinality of theta x. Okay. When the action is conjugate. Theta x is the number of conjugates of x. Yeah, that is this we just wrote. So mod G is this because of this line, right? Where did it go? Yeah. So this is distinct, of course. We are taking only the distinct sums. So now they have broken up this sum into two parts, for which G mod Cgx is 1. Okay, that is if Gx Cgx, okay, all those x such that all such that G is Cgx, that is every element of G commutes with x. So those elements are in the center of G, right? And there G mod Cgx is strictly greater than 1. So these are the two groups they have made. Now x belongs to Zg if and only if theta x is singleton, right? And cardinality of theta x is this, right? So this part is basically, this whole summation is basically Z of G. Okay. So this is the class equation. Okay. We have got the class equation. Clear till now?
belonging to ZG implies theta x, ওইটা কি করে হচ্ছে? theta x টা singleton?
Let x belongs to Zg. Okay. Who asked this, by the way?
আমি.
Pritham, right? Where did it go? Sorry. So suppose x belongs to Gx, and what is theta x? So theta x is Gx G inverse, this set, right? But G and x commute, na, because x is in Zg. So this set becomes xg G inverse, which is x. Okay. Pritham? Okay.
হ্যাঁ হ্যাঁ বুঝতে পেরেছি.
Yeah. So this is the class equation, and let's see one application of this class equation. Okay. So I request you guide to go through these two problems. You have 5 minutes to go through these problems. So you have 5 minutes. Go through this. You gone through it? Hello? Did you go through it? Okay. Pritam, done?
হ্যাঁ দাদা।
Okay. Let's move forward. Observation. Let G be a group X on a set. Then it induces a homomorphism from G to AS. What is AS? AS is the group of all bijection from S to S. It is a bijection, okay? It is a group because if F is a bijection, F inverse is a bijection. If F is a bijection, G is a bijection, then F compose G is also a bijection, and so on. So if G is a group acting on a set S, then there it induces, the group action induces a group homomorphism theta from G to AS, where G goes to tau G. What is tau G? Tau G is a homeomorphism. Wait a minute. Oh, there is a wait. This should be S, huh? Tau G is from S to S. X goes to Gx, huh? And you can see that tau G is indeed a bijection from S to S, because tau G x1 is equal to tau G x2. It means Gx1 equals to Gx2. It means x1 equals to x2. And if y belongs to this should be S again. If y should be belongs to S, then tau G of G inverse y is y. So tau G is again surjection. So clearly you can see that G, they are sending G to tau G. So what is tau G? Tau G is a bijection from S to S. So basically they are assigning for each element of G a bijection in the group of all bijection from S to S. Okay. See that theta of G1 G2, it is tau G1 G2. Okay. Now see tau G1 G2 of X, that is G1 G2 of X, right? But it is nothing but tau G1 what is G1 G2 of X? It is nothing but what should I write? Tau G1 of G2X, right? But that is nothing but tau G1 compose tau G2 of X. Okay. So tau G1 G2 is tau G1 compose tau G2, right? So you get theta G1 G2 is equal to theta G1 compose theta G2. So theta is indeed a group homomorphism. Okay. See, this theta may not be bijective. I mean theta may not be injective. Huh? There is nothing specific. There is no specific comment on the kernel of theta. So they are considering a particular case when G is acting on G itself. Okay. So let's see. So the G is acting on itself by left multiplication, GH. This will induce a group homomorphism from G to AG and so on. The kernel, they are claiming, the claim is that the kernel of this homomorphism is theta. Okay. So if G belongs to cart theta, if and only if tau G is identity, I mean tau G is theta G hour, isn't it? So theta G has to be identity because theta is in because G is in the kernel. So theta G is the identity of AG. Identity of AG is of course the identity map. So tau G of X is X for all X belongs to G, right? Because this is, I mean they are trying to say that tau G of X is identity of X is equal to X for all X belongs to G, right? So Gx equals to X for all X belongs to G. So they are putting X equals to E for all X. This is true for all X now. So you put X equals to E and get that G equals to E. Okay. So now you get an embedding of G into AG, right? Because theta is injective. right? But do you understand that if mod G is n, then AG is nothing but Sn? Do you understand this? That if the cardinality of G is n, then the set of all bijection from G to G is nothing but Sn. Okay. Piyash, is it okay? Mod G is n, then the group of all bijections from G to G, because see, what you are basically doing is you write out G. Okay. Then any bijection from G to G will only permute the elements of G, right? Right. That is, if F belongs to AA, AG, then F is basically a permutation in Sn. Is it okay? Because this is the permutation group of n symbols. So there we have Cayley's theorem, that G is embedded inside Sn. The first proposition that I made in the class, in the start of the class, we have it now. Okay.
generated by এটা কি করে এলো বুঝলাম না।
Sorry. Oh.
Path theta equal to generated by E.
For this particular action. This is for this particular action. Okay. The claim is card theta is E. Okay. So G belongs. So suppose G belongs to card theta. Okay. If and only if tau G is identity. Okay. So tau Gx should be x for all x belongs to G. If and only that is Gx equals to x for all x equals to G, right? This is true for all x, na? So now you put x equals to identity. What do you get? G into identity equals to identity. That is G is identity. So the only element in card theta is identity. Okay. Okay now? Hello.
না দাদা বুঝলাম না এটা।
Why not?
এটা বুঝলাম না ঠিক।
Wait a minute. G belongs to card theta. Okay. So what should be theta of G? What should it be? Identity in AG.
Identity.
Right. Right. So, but what is theta G? We know that theta G is tau G, isn't it?
Tau.
So what will be theta of G of x? That is tau G of x. That is Gx, isn't it? Right? But theta G is identity. So what is identity of x? That is x. Thus we get Gx equals to x for all x belongs to G, right?
ঠিক আছে।
Now you put x equals to E. I mean, in particular, I should write in particular, if x equals to E, then we get right? That is G equals to E. As a corollary, you get Cayley's theorem.
আচ্ছা।
Now there is another observation. Let G be a group. Okay, they are defining a particular type of automorphism from G to G. That is, they are sending x to Gx G inverse tau G. So tau G of x is defined to be, there is a new action. Okay, this is a new thing. They are sending x to Gx G inverse. Okay. So of course tau g is an automorphism of g. Okay. Now consider this action g cross g to g by conjugation, as we were discussing in the first page of this jam. This action will induce a homomorphism because we have seen that any action induces a homomorphism from G to AS. Okay, so theta goes to tau G. Okay, so image of theta is of course AG is nothing but odd G, huh? Automorphism sub G, that is nothing but AG. So image of theta is of course a subgroup of odd G. Now they are computing the theta, kernel of theta. So suppose, kernel of theta contains all G such that tau G is identity. That is, all those G belongs to G such that Gx G inverse is X for all X belongs to G, right? That is the center of G, na? All those G that commute with every X in G. That is the center of G. So there is an injective map from theta tilde from G mod ZG to odd G. Okay, by first isomorphism theorem. Okay, these tau G, I mean this sort of tau G's where tau G is from G to G and tau G is defined to be X going to Gx G inverse. Gx G inverse, okay. Okay, Gx G inverse. So these are called inner automorphisms. Okay. So all such things, I mean tau G, all those I should write this is in G where tau G, set of all tau G where tau G is an inner automorphism. Inner automorphism. This is a subgroup of odd G. Okay. So each subset of G, subgroup of G, is be the set of all left cosets of H in G. Okay. So S is nothing but G mod H. They are acting G on S. Let's see what they get. Left translation. They are sending G comma XH to GXH. This action will also induce a group homomorphism from G to AS. All of you can see my screen, na? Hello?
Hi, Dada.
Okay. Okay. So yeah, so G is going to tau G. Okay, that is the theta here. Tau G is xh going to gxh. Tau G is clearly an automorphism of S. Okay, so they are again computing the kernel gx so on, and they get xg x inverse for all. Okay, so gx
তো টাউ জিটা অ্যাকচুয়ালি কিভাবে ডিফাইন্ড বুঝলাম না, কারণ আগেরটাই তো জি এক্স জি ইনভার্সে গেল।
yeah, the action
টাউ
was different, na?
আচ্ছা
The
আচ্ছা
action was different. Tau G depends on the action.
আচ্ছা আচ্ছা
Okay. Okay, so again they are taking x equals to e in particular. So g is inside h. So card theta, right? Putting x equals to e, they get gh equals to h. So g is in e. So card theta is a subgroup of h. Okay. Now they have a corollary. That is, h is a subgroup of g, and g is to h is n, and no non-trivial normal subgroup of g is contained in h. Then G is isomorphic to a subgroup of Sn. H subset of G, G mod H is n. I mean G is to the index of H in G is n. No non-trivial normal subgroup of G is contained in H. Then G is isomorphic to H. Okay. See what happens. Card theta is in H. Okay. But no non-trivial normal subgroup is in H. So card theta is E. Or card theta is H, right? So card theta is either E or card theta is H. If card theta is E, then G is inside this. But how are they excluding the case where card theta is H? Wait a minute. Oh, H may not be normal, na? No non-trivial normal subgroup is contained inside H. So if card theta is H, then H is normal in G, and H is of course contained in itself. So there is a non-trivial normal subgroup of G which is contained in H. No, this is not true. So card theta is identity, right? I mean card theta is trivial. H subset of G, G is to H, again H subset of G, G is to H is P, where P is the least prime which divides G, then H is normal in G. I hope you have seen ton of this type of problems in NET and JAM.
একটু নিচে নামা হবে,
নিচে মানে
একটু নিচে নামা, উপরের ওইটা দেখতে পাইনি। হ্যাঁ ঠিক আছে।
Okay. So H be the set of all left cochets of H in G. Again they are again doing that same action. This action will induce blah 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 blah. G goes to tau G. Now card theta is inside H. Okay. Card theta is a normal subgroup of H. I mean card theta is a subgroup of H. Then what is G mod card theta? G mod card theta is G mod H into H mod card theta, right? G mod H is P. So P is P into H mod card theta. Now G mod card theta divides P factorial, na? Right? Because G mod card theta is inside HP. Isn't it? The first isomorphism theorem. G mod card theta, there is an injection from G mod card theta to SP. So G mod card theta must divide P factorial. So P into this must divide P factorial. You cancel this out. So H is to cot theta should divide P minus 1 factorial, right? Let Q be a prime such that, Q be a prime factor of this thing, okay? Q a prime factor of this thing, then Q divides H is to cot theta. Now see, Q divides H is to cot theta, right? This implies Q divides mod H. This implies Q divides mod G, okay? But if Q divides mod G, then Q divides, okay, this is 1, okay? This is 1. And since Q divides P minus 1 factor, Q divides this, na? If Q divides this, then Q must divide this as well, because if Q divides this, then Q divides this as well. Since Q divides P minus 1 factorial, Q has to be a prime less than P, which contradicts 1, right? If Q divides G, then Q has to be greater than P, na? Because P is the least prime dividing G, which is a contradiction. Thus we get there is no such Q. So H is to cot theta is 1. So H is cot theta. H is normal in G. Okay. Okay. So these are a few applications of group action. We will do Hungerford 91, 92 on next class, but for the timing we will proceed. This is not only 1 and 15, huh? This is 1 to 15. Because I have come across a professor who shared his experience. He told his students to do 1 to 15. Okay. And they did 1, 2 and 15.
দাদা বলছি 1 থেকে 15টা কি মানে অঙ্কর নাম্বার বললে?
Yeah. Page 91, 92. Hungerford, this is. See, you can solve Damit food as well, okay? But I am preferring Hungerford because this is more precise. Damit food is like a Mahabharat. I don't think I can complete it.
হ্যাঁ।
What is there? Lemma. This lemma will we use it anywhere? Cauchy's theorem. A group of order h order b to the power n acts on a set this. Okay, we will prove this lemma, but Cauchy's theorem we won't prove. We will assume it because we all know it. Okay. Okay. Let's prove this lemma first. So they are saying if G is a group of order p to the power n, if H is a group of order p to the power n, p prime acts on a finite set S, and if S naught is the set of all x in H such that Hx is x for all H in H. Okay, don't confuse it with the stabilizer. Okay, the definition of stabilizer of x is all those G such that Gx is x. This is a subgroup of G and S naught is a subset of H. So don't confuse between these two. So they are saying all H's, all X belongs to S, which are fixed by every element of the group. Okay. They are saying that mod S is congruent to mod S naught mod P. Okay. Let's see. So S is union theta x distinct orbits. We have seen this. Note that when is theta is singleton x? when is theta x singleton x? Theta x is singleton x if and only if hx is x for all h in h, right? That is if x belongs to S0, right? So theta x is singleton x if and only if x belongs to S0. So mod S is, they are again breaking it up like the class equation. Now they get this, right? This whole sum contributes to the cardinality of S0. And this, what is theta x? We have shown that theta x is h is to the index of hx in h. Okay. Now see that h is to hx, this thing is divided by p, na? Right? Because mod h is p to the power n. So this is congruent to 0 mod p, right? Hence you get this minus this mod s. So you get, this is obvious, na? Because you get mod s minus mod s naught is equal to this thing where every term is divisible by p. Okay. Cauchy's theorem says that if G is a finite group whose order is divisible by a prime p, then exists an element A such that order of A is p. You can see the proof, but I will skip it for the time being. A group in which every element has order of a power or some fixed prime p is called a p group. Okay. The definition of a p group is every element in that group must have order which is a power of p. This is a small observation. Yeah, these are very useful things. See, you have 2 minutes. Read this from definition to Lagrange's theorem. Read this. This thing, the thing on the screen. 2 minutes you have. give me 1 minute. Okay, so let's move on. Here is another lemma. Remember this result, okay? That mod S mod S naught is S congruent to S naught is mod P. So they have taken H to be a P subgroup of a group G. Okay. Then NGH, you know NGH? Piyash, do you know the definition of NGH? Normalizer of H, huh? NGH is, Piyash, are you there? All those G belongs to G such that GH, G inverse is H. Okay. So S be the set of all left cosets of X in H in G. They are acting H on S. So S is G mod H. Okay. Mod S congruent to S naught mod P by key lemma. So what is S naught? They are trying to figure out what is S naught. So suppose XH belongs to X naught. Then HXH is XH for all H belongs to H. That is X inverse HX is belongs to H is for all H belongs to H, right? So clearly X belongs to NGH. Thus S naught is NGH is to H. Okay. XH belongs to S naught if and only if X belongs to NGH. If and only if XH belongs to NGH quotient H. Okay. So mod S naught is NGH is to H. Okay. Thus G is to H is congruent to NGH is to H mod P. Done. Observation: P divides NGH. If P divides GH, then P divides NGH. Okay. That implies NGH is not equal to H. Okay. Syloh's first theorem. We will read the statement. Okay. We won't prove it. Let G be a subgroup of order P to the power alpha m such that GCD of P and M is 1, P is prime. Then G contains a subgroup of order P to the power I for 1 less than equals to I less than equals to alpha I mean for each I this happens, okay? And every subgroup of G of order p to the power I is normal in some subgroup of order p to the power I plus 1. Clear? The statement is clear? Let's go through it again. This is the order of G. Then G contains a subgroup of order p to the power I for each I, and every subgroup of G of order p to the power I is normal in some subgroup of G of order p to the power I plus 1. They will proceed by induction on B and so on. The maximum P subgroup, that is the subgroup of order p to the power alpha, is called the Sylow P subgroup. Okay. So clearly, if there is only one Sylow P subgroup, then that is a normal subgroup. See, if there is only one Sylow P subgroup, then suppose H is the Sylow P subgroup, then both H and XH X inverse, they have same order, na? And they are both Sylow P subgroups, but they should be equal for any X. So you get this for any X belongs to G. Thus H is normal in G. Again, the second Sylow theorem is so H is a P subgroup of a finite group G. P subgroup means a group of order p to the power I, and P is any Sylow P subgroup of G. Then there exists X such that H is contained in XP X inverse. Okay. In particular, any two Sylow P subgroups in G are conjugate. Okay. So this was Sylow's second theorem. Third theorem is, if G is a finite group and P is prime, then the number of Sylow P subgroups of G divides mod G. We sometimes call it NP, and it is of the form Kp plus 1. That is, NP is of the form Kp plus 1. Okay. You can go through the theorems, okay, but I'm skipping them. I mean, for the proof. Yeah, classification. These classifications are very much important. Let's go through the classifications. So they are saying that P is a prime and G is a group of order 2P. Let's see what they get. By Cauchy's theorem, there is an element A and B in G such that order of A is 2 and order of B is P, right? There exist two such elements. Now G is to K is 2. Do you know then K is normal in G? Is it clear to you that if G is to... Is everyone okay with the proof that if there exists a subgroup K of G such that G is to K is 2, then K is normal in G? Is it okay? See, you see left cosets. I mean, if you see left cosets, there are only two, K and GK. Okay, but G not equal, doesn't belong to K. And if you see right cosets, then they have only two again, G and KG. So we know that G is K disjoint union GK from this, right? From this. And from this we get G is K disjoint union KG. Combining these two, we get GK equals to KG for all G doesn't belong to K. So you get GKG inverse is K for any G belongs to K. Okay. So group of index 2 is always prime. And you can also use that theorem that 2 is the least prime dividing the order of G. Okay. There cannot be a prime smaller than 2, na? So you can use that as well. So by Cauchy's theorem, blah 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 blah. Since K is normal in G, HK is a subgroup of G. So mod HK is H mod H into mod K by mod H intersection K. Okay. But if you realize that GCD of mod H and K is basically 1, because mod H is P and mod K is P and mod H is 2, na? So they have no element in common, because if they have an element in common, it divides, the order of that element divides. Okay. So mod H intersection K divides H and K both. But since these mod H is 2 and mod K is P, they are co-prime, so mod H intersection K is just 1. So mod HK is P. Thus you get, mod HK is 2P. Thus you get HK is itself the whole group. Okay. Since K is normal in G, AB A inverse is in K. I think K was, yeah, K is generated by B and H is generated by A. There are some computations. So AB A inverse is in K, right? Which is generated by B, which is a cyclic group. So AB A inverse is B to the power I for some I. since order of A is 2, sorry, what is that? How did they get there? How did they get there? We have B equals to A. Oh, this is very easy. This is identity, na? These are identity. A square is identity. So they have just written B in this way. So now you get this. You get this putting V to the power I instead of this. But what is this? You take A, B, A inverse, multiply A, B, A inverse, and so on. You get only A, B to, if you multiplied I times, you get A, B to the power I, A inverse. So that's what they have written. But A, B to the minus 1 inverse I is B to the power I whole to the power I, that is Bi square. Okay. But then you get B equals to B to the power I square, that is B to the power I square minus 1 is E, so P divides this. So P divides I plus 1 or I minus 1.
So P divides I square minus 1, ওটা কি করে হলো?
B to the power something is E, so the order of B must divide this, na?
আচ্ছা আচ্ছা, P টা মানে order of B ছিল।
B is the generator of K, na?
আচ্ছা,
So I is, so P divides I plus 1 or I minus 1. Remember, I is less than P. Huh? You take there, I was, yeah, I is this. So I is either 1 or P minus 1. So either AB A inverse is B, then AB is BA. Then order of AB is 2P, then G is just Z mod 2PZ. If it is P minus 1, then it is probably the dihedral group. Okay. So these are the classification of order group of 2P. The next thing is that we do groups of order PQ. So for P less than Q and PQ primes, G has elements of order P and Q, I mean Q respectively, blah 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 blah. H is generated by A, K is generated by P. P be the least prime dividing G, of course, because G is of order PQ. Then K is normal in G, because K is of index P. So HK is a subgroup of G. Then again you see mod HK should divide, mod HK is this, H intersection H, mod H intersection K should divide mod H and mod K, but since the GCD is 1, mod HK is 1, again you get G is equals to HK. So again by similar computation you get B equals to B to the power, B equals to B to the power I to the power P. So you get B to the power I to the power P minus 1. Order of B is Q, so Q must divide this. So I to the power P is congruent to 1 mod Q. Okay. So this is one. We look into some special condition. If P doesn't divide Q minus 1, then G is cyclic. We will go there, just a minute. Where is it? Not much content is there. Well, this is something we will use left, right and center, that if mod G is PQ, where PQ and primes and P doesn't divide Q minus 1, then G is cyclic. So again you get two elements A and B generated cyclic subgroups H and K and so on. K normal in G, the number of silo subgroups P is 1 plus Kp, right? So 1 plus Kp should divide PQ, but 1 plus Kp can't divide P, na? And GCD of P and 1 plus Kp is 1. So 1 plus Kp should divide Q. This is the thing. If mod G is P to the power alpha into M, then NP, which is the order number of silo P subgroups, it cannot, it should divide M, na? Because NP and P to the power alpha, they are co-prime. So Sylow's theorem not only gives us that NP should divide G, it gives us NP divides the index of the silo P subgroup in G. Okay. So you get there is only okay. So 1 plus Kp divides Q, so we get that. I think we will get P divides Q, which is not possible. So 1 plus Kp is 1. So there is unique P silo subgroup and unique Q silo subgroup. Thus G is isomorphic to the direct product, external direct product of H and K. By Chinese remainder theorem, you get this. We don't need this, we don't need this, we only this part. If P is a silo P subgroup of a finite group G, then NGP is NGP. Clear? Normalizer of NGP, normalizer of P is basically normalizer of P. Okay? Okay, so how do we prove it? So suppose X belongs to NGP. Okay, that means X NGP, X inverse is NGP, right? By definition of NG, by definition of normalizer, right? See, P is a subgroup of NGP. So XP X inverse is a subgroup of X NGP X inverse is equal to NGP. So XP X inverse is a subgroup of NGP, but P silo subgroup, but P is silo P subgroup. So NGP is also of NGP also, yeah, of course, because P is the biggest, biggest P subgroup. Thus we get P is normal in NGP. So XP X inverse is P, which means X belongs to NGP. Clear? Clear? Okay, so see, that's it for today. From the next class onwards, we will start solving problems of Hungerford. First we will do 91, 92 page. See, I have gone in a Rolls-Royce pace, I know. So please go through the theory. If you are anywhere stuck, please let me know. So this is the first thing we will do. This is the first exercise, and then we will do the next exercise. Classification of finite groups a little bit. Isomorphism. Semi-direct product we don't need for the time being. Abelian, Hanna, important and solvable groups, these are very much restricted. We will see that. Okay, so that's it for today.
দাদা এই আজকে যে নোটসটা লিখলি সেটা একটু খুলবে একবার?
This one, yeah.
ফার্স্টের দিকটা।
I will send you these things by the way. Yeah, please.
দাদা বলছি এখানে যে মানে লেফট রেগুলার রিপ্রেজেন্টেশন মানে এটার মানেটা বুঝলাম না।
Oh, that's a trick. That's a trick to prove G is embedded inside Sn, okay? And how did they prove it? What was the proof by the way?
দেখতে পেলে ভালো হবে।
Wait a minute, where did the proof go of Cayley's theorem? I pointed here. See, if you understand one thing, they are assigning G to tau G, isn't it? So for each G, they are assigning a bijection in AG, right? This is called left regular representation.
মানে এটাকে লেফট বলছে কেন?
Because this is a left action.
ও আচ্ছা আচ্ছা।
If you want
ঠিক
a
আছে
detailed proof, wait a minute. You can ask for a detailed proof. Just give me 1 minute. Just give me a minute. I hope Rahul, can you find out the proof of Cayley's theorem in Damit-Frew? Can somebody tell me where is it? Okay, let's find in the index. Cayley's theorem, Cayley. Cayley's theorem 118. Okay, so this should be our 135 maybe. Yeah, this is Cayley's theorem. They haven't given left regular representation, left multiplication. Where is left regular representation by the way? Yeah, this is it. Just read this section, okay? Not the whole section, you don't even need that. Just this is left regular representation, okay?
ঠিক আছে তাহলে।
They basically do, suppose you take G belongs to G, okay? Then what is tau G of Gi? This is G into Gi, okay? This has to be some G's, na? So then you define tau G, then you define tau G to be sigma G, where sigma G sends I to J, okay? The sigma G is in the element of Sn. That's the whole point. Just read this. Damit-Frew is a book which is very easy to read. Okay, this is the same. 4.2 I think. Okay, so let's conclude today. Short one.